What would happen if you built a ground plane with just one radial? Let's investigate that this time on the channel. So what would be the purpose of building an antenna with a one radial? The chief reason for doing that would be ease of deployment. So technically, an antenna with one radial is not a ground plane. It's an L antenna. It takes at least two radials to make a ground plane. Here's a 10-meter full-size antenna that would have two radials and would be considered a ground plane. You can see the pattern is pretty much omnidirectional. A slight bit of gain broadside to the radials and only about 1.3 dBi gain. This antenna is about 11 or 12 feet above the ground. And what if we were to build this as a trapped vertical? And we would use one trapped radial to cover three bands, which we could do. That antenna would look something like this. So we can see our traps. There's traps in the vertical section, there's traps in the radials, in the single radial. And the pattern changes dramatically. And an L antenna is not going to look like a ground plane. You can see it's not a good looking pattern, but it still has 1.3 dBi gain at 20 degrees, perhaps even 15 degrees elevation. So this antenna would work fine, although it is directional in the direction of that single trapped radial. And let's go ahead and check this antenna on the other band. So we'll have, here's 20 meters, showing about 0.8 of dBi gain at 25 degrees elevation, perhaps 20 degrees if we were to check it lower. And once again, slightly directional, but it would work. And then on 40, we can see the same thing. So down about half a dBi gain. But also you can see as you go lower in frequency, this antenna starts to perform more like a ground plane. And it's just simply because wavelength and above ground. So the above ground distance isn't changing, but the wavelength is. It's getting larger. So on 40, this actually works pretty good. You can see the current band takes the entire antenna at 40 meters. The traps are basically invisible at 40 meters. So this antenna at full size with two radials would look like this. And you can see it does have a bit better omnidirectional pattern, but the gain is almost the same. There's almost no difference in gain between a full-size antenna with two radials and a trapped radial antenna with one radial in this example. All right, we're stating our goal as a multi-band vertical antenna. Specifically, we want to cover three bands. We want to cover 10 meters, we want to cover 20 meters, and we want to cover 40 meters. And there's a variety of ways to get there. We could go columns route and do what's technically known as a fan vertical, where you have multiple wires running vertical from a central point, a central feed point. And those work just great. And I had thought about going that way, but I'm kind of a fan of these little items right here. These are known as coax traps. And in general, RF traps are pretty cool little devices. But the reason I like going with this method is once you get these traps built and tuned, then the rest of the antenna construction is relatively simple. So this is the hard part in building a trapped antenna, either a trapped horizontal dipole or a trapped vertical. Anyway, once these are done, the rest is easy. So if we look at, let's say, a 10-meter antenna, the simplest 10-meter antenna that we could possibly build would look something like this. We would have a quarter wavelength vertical section, and we would have another quarter wavelength vertical section, and we would feed it in the middle with coax. And that's what's known as a vertical dipole. And they work very, very well. They're not ideal for what I want to build because let's figure 10 meters, which would be the shortest band that we're dealing with. We're still dealing with 8.5 feet on each leg of that dipole. And between this and the ground, there has to be a certain amount of space, because if we get too close to the ground here, it diminishes the effect that this quarter wavelength section down here will actually perform. So not the best idea to start with this unless you can get it way up in the air. And then we're still left dealing with 20 meters and 40 meters, which requires a lot longer lengths of wire. So although that would work, that's not where we're going to be building today. So then another option would be something like an antenna that was an L-shaped design. And once again, that would work great. It fixes our ground problem down here because we're now running this wire horizontally. But there's an impedance consideration here. Actually, there's two impedance considerations. In a vertical dipole, the straight dipole that I drew earlier, the impedance would be a little bit too high for a 50 ohm match. On this one, it's going to be a little bit too low for a 50 ohm match. Anytime we have this 90-degree thing going on here, it's probably going to be less than 50 ohms. Not a great match to a transmitter. So that's probably not going to work for us either. But with a slight modification to this, we can get where we want to be. So instead of putting that at 90 degrees, let's just change the angle somewhat and bring it out here like this. Now this is actually a workable design because it's a compromise between the vertical dipole and the 90-degree ground plane-ish L-shaped antenna that we just drew. And the impedance match will be fantastic. We can change the direction of this radial and tune it so we can get a perfect 50 ohm match. So bringing it this way would lower the impedance, and bringing it down this way would raise the impedance. We can find a happy medium. Now, this antenna, you notice I've only drawn one radial, and that's intentional. That's how I'm going to build mine. I'm just going to have one radial. And the reason I'm going to do that is because most of my contacts are east of me. I'm pretty close to the Pacific Ocean. So 80–90% of what and who I talk to are east of me. So I can stand a little bit of directionality in my antenna, which this will be directional slightly in that direction. Now, if you, let's say you lived in Texas and you wanted the capability to go either direction, then what you would do is you would just make another radial, exactly the same length as this one, and what you would end up with is a mostly omnidirectional antenna. And I say mostly because there'll be slight gain broadside to this antenna, and there'll be slight nulls off the ends, but we're only talking about half of a decibel. It's not very much to be concerned with. It's mostly omnidirectional. So you really only need two radials to achieve that. If you wanted to reduce those nulls and make it truly omnidirectional, then you would just add a third or maybe even a fourth radial. But that's complexity that I don't want to deal with, so I'm not building mine that way. So now this is just a single band antenna at 10 meters. What do we have to do to this to make it multi-band? Using coax traps. Let me change the scale of this a little bit. So if we want to build a multi-band and we want to employ these little devices, then what we will need to do is we cut our 10-meter lengths of wire, and then we're going to put coax traps that are tuned to block 10-meter RF. And what you'll do with these is you'll tune them to be resonant just slightly outside of where you actually transmit. So in my case, I really don't do CW or digital mode, so my 10-meter world starts at about 28.300. So I'm going to tune these to be resonant at like 28 megahertz flat. That's just below where I'm actually going to be transmitting. And the reason you do that is because these have losses right where they're resonant. So at 28 megahertz flat, there'll be about a dB of loss. But if you increase your frequency to 28.300, the loss diminishes down to around half a decibel or maybe 0.6 of a dB. So you minimize those losses a little bit if you do that. So these should both be tuned for 28 megahertz flat, and I'm going to check them here in a little bit with the Nano VNA to make sure. Okay, so we put our 10-meter traps in, and then what we would do is we'd add the lengths of wire again. We put in more traps. And these traps would just happen to be tuned for 20 meter RF. So at 20 meters or 14 megahertz, these will block RF. And it will use this full length of wire for 20 meters, but it will stop right here. Now, another advantage of using traps is every one of these traps will act like a loading coil on the lower band behind it. So this actually shortens the 20 meter section of wire that we need by a few feet. So on both the vertical leg and the radial, we won't need quite as much wire as we normally would. It'll shorten it by several feet. For instance, let's go ahead and finish this antenna. We're going to put some more wire out here. And this will be for the 40 meter section. So this is 10 meter. And then this is 20 meter. And then this is 40 meter. And it'll be the same on the vertical. A typical 40 meter radial or vertical section is going to be somewhere around 34 feet if you don't have traps installed. But when you put those traps in, this number gets reduced because of the loading coil effect of the traps. This will actually be somewhere down around 25 feet. So it makes the overall length, height of the antenna much, much shorter, which is really a good thing because you can imagine making a 34-foot vertical section that's freestanding without radials is quite a challenge. So by shortening it down to 25 feet, that becomes more of a reality. And we'll talk more about that once we get out to the garage and look at the materials that I'll be using to build this with. This antenna is going to be built out of 14 gauge wire. So what I'm going to be using is just ordinary 14 gauge THHN insulated wire. And it will handle all the wattage that I need for it to handle. These traps are built with either RG58 or RG8X coax, which will handle plenty of power. So should work just fine. Now, there are losses, like I said, in these. There's about half a dB of loss. But even in a fan vertical, there are losses because when you transmit on a certain band, some of that radiated energy is going to go into the wires that are tuned not on the band that you're transmitting on. So there are losses in fan verticals too. So it shouldn't be a big deal. Either way, it's going to have slight bit of loss. Every multi-band antenna has associated losses. There's just no way around that. But this should be a pretty good antenna to build because it's going to be relatively short for a vertical that will work on 40 meters. And because it uses only one radial, a trapped radial, it will be much simpler to deploy in like a POTA situation or a SOTA situation. And I'm going to set it up to be that way so I can run it at home as a full-time vertical. And then if I need to take it out in the field, I'm going to have it set up so that I can pull it down and roll it up and take it with me wherever I need to go. All right, that's what we're going to be building. And the first thing I want to do is check these traps and make sure they truly are resonant where they're supposed to be resonant. So I'll grab the nano VNA and we'll do that. Now, I didn't cover coax trap building in this video, but I have in the past. So I'll put a link to that video and you can check that out. And then also in the comments down below, there's a resource on the internet. It's K7MEM is his website. And it's by far the best resource for trap building that I've found. So that'll be in the comments down below. And that'll show you everything you need to know to build coax traps. Okay, we've got the nano VNA calibrated. Our frequency range for calibration was 13 to 29 megahertz. That should give us plenty of headroom for measuring a 28 megahertz trap and a 14 megahertz trap. So we should be good there. And now what we're going to do is we're going to narrow that range down. So we're going to check our 10 meter traps first. Let's go 27 megahertz to 29 megahertz. And hopefully these traps will be resonant right in the middle of that range. And it looks like that trap is resonant at 28.1 megahertz, which is below 28.3 megahertz, so we're good there. Trap number 2. Slightly lower at 27,940, but once again, good enough. Now, if these needed to be adjusted, you can change the adjustment frequency by moving the coax in and out, closer together and farther apart. So if you wanted the trap to be lower on frequency resonance, you would get them closer together. And if you wanted to raise the trap resonance, you would separate them a little bit. And then once you do that, just figure out a way to lock that down so it can't move anymore. I like to use clear enamel for that. Just give it a couple coats of clear enamel, let it dry, and mask off the terminals, obviously. You don't want paint on those. But mask these off with masking tape, give it a couple coats of clear enamel, let it dry, and then the wires will be locked down. Okay, on to our 14 megahertz traps. We'll use 13 megahertz to 15 megahertz. And once again, we're hoping to be resonant right in the middle with a 20 megahertz trap, or I'm sorry, 20 meter trap, 14 megahertz trap. That one looks good. It's 13,980 megahertz. And that one's 14 megahertz on the dot. Once again, you can adjust that by moving these in and out and then lock it down with some method. Heat shrink works good. Tape would work, but it probably wouldn't last forever. Epoxy or enamel would be the other two options. So, all right, traps are perfect. I'm going to go ahead and figure out what my wire lengths need to be, and we'll cut those and get started building. Okay, so now I'm going to start working on the wires, the actual wires for this antenna. And these two wires are going to be from the feed point of the coax up to the 10 meter trap and out to the 10 meter trap on the radial side. And then these two wires are going to be the wires between the 10 meter trap and the 20 meter trap on both the vertical and the radial. And I believe that I've cut these wires a little bit long. And the way that I determine the length is, and it can be quite tricky when you're working with trapped antennas because, as I mentioned, the traps act as loading coils, which can shorten everything up, and it's kind of hard to figure out exactly what those dimensions are. But I've already built a 10-20-40 vertical that used full-size radials, and it was a trapped antenna. The only difference was that that antenna was in PVC Schedule 40 pipe. So it used, for the most part, it used insulated wire like this, and it used the same traps, same style of traps anyway. And what the concern is here is that the velocity factors have stacked. So we have a velocity factor with insulated wire, which makes it slightly shorter than what you calculate. And then just sliding that insulated wire inside of PVC Schedule 40 pipe also changes the velocity factor. It makes it even shorter yet. So I'm guessing here that the change is about 5%. That's probably excessive, and they'll probably be too long, and I'll probably have to trim them. So that's the hope here, that we're a little bit too long, and that I have to trim. And that's the reason I haven't cut the wires that go from the 20 meter trap out to the ends of the antenna, both on the radial side and the vertical side, because I kind of want to determine what these lengths will be first so that I know what the exact length of wire will be from the top of the 20 meter trap to the tip of that 20-foot section of fiberglass that I'm going to be using. So this is all guesstimation. I need to really get it in here and find out. But what I'm going to do is I'll go ahead and attach eyelets to these, and on one side I'm going to go ahead and solder that eyelet and put heat shrink on it for strain relief, and it'll be a finished eyelet. On the other side, I'm just going to wrap the copper wire on the eyelet as a temporary setup so that I can undo that and shorten it if I need to. So we'll go ahead and get started doing that. I'm not going to give the lengths of these wires just yet for the simple reason that I might have to adjust them multiple times. And if I do, I don't want to confuse anybody by giving them the dimension that I'm using here, because that dimension will most likely change. I'm just using ordinary crimp style eyelets, but I really don't need the insulation, so I just heat those up a little bit just to soften the plastic, and then just pop those off. And the way that I like to do this is I just like to cut it a little bit long and then fold it over. And then just give a little bit of a twist, like so. And then solder it. And then some heavy heat shrink just to give it a little bit of strain relief. And that side I'm just going to twist like that for now. As I shorten this, if I need to shorten it, once I get to the correct length, then I'll solder it. Okay, I'm going to do the rest of the wires just like that. No need to film that, so I'll be back in a minute. Okay, we've modeled it, we've sketched it, we've cut the wires, we've built the coax traps, and in the next video I'll put it all together and we'll test it out. Thanks for watching.